So I wanted to make a video both clarifying the definition of the different types of mechanical advantage and also go over some rules, clarify some rules of the different types of levers. So let's go ahead and start by discussing the second class lever. Now the second class lever has some rules, as we've learned. So let's go ahead and draw ourselves a second class lever here. Give it a fulcrum, and as we know FR is on the inside, so we'll go ahead and write FR here. And the force effort is, of course, fighting it on the outside. Well, because the force effort is always farther away than the force resistance to our fulcrum, that means our distance effort is always a bigger number than our distance resistance. In other words, in a second class lever, this is always true, that our distance effort is greater than our distance resistance. Well, since the equation goes dE over dr, this means that dE over dr is always, well, let's go ahead and say, if dE is bigger than dr and it's always on top, we say 5 over 1. Okay, well, this is a number bigger than 1. And it doesn't matter what number goes on top because the number on bottom has to be smaller in a second class lever. And this is the idea I want to drive home, is dE over dr is always greater than 1. Therefore, in a second class lever, the mechanical advantage is always greater than 1. And when we have a system with a mechanical advantage greater than 1, it means we have a force advantage. And of course, a distance disadvantage. And this is the way, or sorry, distance disadvantage. I don't know if I said that wrong. But this is the way it always works in a second class lever, is you have a distance disadvantage. You have to travel farther to increase your force or give yourself a force advantage. And then, since a third class lever is basically the exact opposite of a second class lever, let's talk about that one next. And let's draw the same system where we have a bar and a fulcrum off to the right. But this time, let's put force effort on the inside, the way it works in a third class lever every single time. And the force resistance is on the outside. What does this mean? Well, this means that dE is always closer to the fulcrum than dr is in a third class lever, which means that dE is always a smaller number than dr, so less than dr. Well, if we follow the same rules as before, we know dE over dr, dE is always on top of dr in our mechanical advantage equation, so it doesn't matter what number we put on top, the number on bottom will always be smaller. So if we go back and we change this number to 16, I'm sorry, bigger, the number on bottom will always be bigger, so we can make this 20. And we can put whatever number we want on top. We can put 8 over 5, or I'm sorry, it can't be 5, but it could be 15. The point is that dr is bigger than dE. We could put any number on bottom that's bigger than 8. We could put 9. Or we could put 52 on top, but then we'd have to put a bigger number on bottom. The point is we'd always get a fraction. In other words, dE over dr in a third class lever is always less than 1. Which of course means in a third class lever the mechanical advantage is always less than 1. And of course this means we have a force disadvantage anytime we have a mechanical advantage less than 1. Which means, by definition, in a third class lever, we have a distance advantage. And so anytime you see a second class lever, you can automatically assume that the mechanical advantage is greater than 1. You already know that. Likewise, for a third class lever, if you see one, you already know the mechanical advantage has to be less than 1 by definition. Now, if you're OCD like me, you might be wondering, why did I skip the first class lever? Why am I saving this for last? Well, the reason is because the first class lever doesn't have a rule like the second and third class lever, where it's always greater than 1 or it's always less than 1. In fact, I can draw an example of each where the fulcrum is in the middle and FR and FE are on either side, like the rules of a first class lever. So maybe I have FR here on the right, super close to the fulcrum, and I have force effort here on the left, far away, which is by definition a first class lever. Or I can have force effort here closer to the fulcrum and my force resistance farther away from my fulcrum. Well, in this first example, we can say that dE is clearly greater than dr because it's farther away, which means, looking back here, just like in this example over here, in this example, our mechanical advantage is greater than 1. And in this second example of a first-class lever, we can see that Fe is much closer to the fulcrum. So that means dE, by definition, has to be smaller than dr. And then following the same logic over here, if dE is smaller than dr, we can assume that the mechanical advantage in this type of first-class lever, this example of first-class lever, is less than 1. And actually, let me go ahead and bring this down a little bit so I have some room to write in between each one. But this means I have a huge force advantage. Well, not necessarily huge, but I have a force advantage sometimes in a first-class lever. And sometimes in a first-class lever, I get a distance advantage. And sometimes in a first-class lever, you will get greater than 1, and sometimes you'll get less than 1. And then sometimes, it'll get really confusing, you get a mechanical advantage equal to 1. And that's where dE is equal to dr. So they're the same distance. So it wouldn't matter what number I put on top. If I put 5 on top, dr is equal to that. We get 5 over 5, we get 1, and that'd be true for any number. And so let's go ahead and draw this example for us where we have the fulcrum in the middle and we have Fe and Fr equidistant. And what does this do? Well, what it tells us when we have a mechanical advantage equal to 1 is there is no advantage. Well, what does that mean? Well, I mean, in this system, there is no force advantage. There is no increase or decrease in force. There is no distance advantage. There is no increase or decrease in distance. There is no change in force or distance whatsoever when it comes to the work equation happening. What it does do is change the direction of the force. I push down, which would lift up, like a seesaw. And we'll talk about why we would do this in our next lesson on our next machine.